Yeah, welcome to this Docent lecture given by Claudia von Brömssen to become docent in biometry. And welcome all of you in the room. It's nice to see it's almost full. And also for you online. The procedure of the lecture today is that we have total allocated time of 1 hour. Within this hour, first Claudia will present her research during 30 to 35 minutes. After that, we open up for questions. First, we have the topic representative, then the pedagogic representative, and followed by the delegates from the Docent nämnden. If we still have time, there will be available open for questions from the audience as well. And the representatives attending this lecture is myself as chairman. I'm Professor Björn Winnerås, and I'm Professor in Environmental Engineering, and I'm head of Department of Energy and Technology. We have the topic representative, Magnus Ekström, who is online, and he's guest professor in mathematical statistics at SLU in Umeå. We have the pedagogic representative, Alexandra Durso, that is pedagogic developer here at SLU. And then we have Docentnämndens representatives, Anna Schneider, professor at the Department of Molecular Sciences. We have Lisbeth Levan, docent at the Department of Soil and Environment. And we have Pia Nilsson, docent at the Department of Economy. And we have the faculty represented here by both the Dean, Professor Thorleif Härd, and the Pro-Dean, or Pro-Decan, Professor Sara Hallin. And now to the person in focus, Claudia von Brömssen. She has been working at our department since 2016, but have been at SLU since 2007. She's originally coming from Austria and got her master degree in statistics at the University of Vienna. And she got her PhD in statistics at Linköping University. The main focus in her current research is environmental statistics, or statistics in environmental monitoring and assessment. And she will now present her docent lecture, Temporal Events in Environmental Data, if, when, where, and why. Please.
Thank you. So yes, I named my presentation Temporal Trends in Environmental Data, if, when, where, and why. And this actually started when I was a student in statistics at the University of Vienna, and I wanted to do a semester abroad. And it was very easy to come to SLU here in Ultuna, so I did that. And obviously SLU does not have a statistics program, so there were not so many courses for me to take. If I remember it correctly, there were 3. And there was one specific course that I really didn't see any point in taking. I couldn't see how it would fit into my career. It seemed a little bit odd, but I needed the credits, so I took it anyway. And the course was called Time Series Analysis in Environmental Monitoring and Assessment. And this course, or maybe my lack of choice, is the reason why I'm here today. So why didn't I see environmental statistician as a career choice when I was studying statistics? Well, there is no labor market in this. There are very few jobs announced, and they don't talk in other undergraduate statistics programs about environmental statistics, because if you want a secure job, you go into medicine. So the focus is on medicine, which is really a pity, because there's a lot of data in environmental studies, of course, and also the statistical problems that we face, they are not really trivial. There's a lot to do. But we can start looking a little bit on what sets environmental data aside compared to like more regular type of studies that we make. And if you remember your undergraduate first statistics course, you will remember us talking a lot about assumptions. So it's really a question about assumptions, because we tell you that, well, you need to have independent observations. You should really need to assume some data distribution, perfect if it's normal, or something else that works well, some theoretical data distribution. You would really like to have linearity or some other functional form. Maybe you want an exponential function, but you need to define which kind of relationship you want to model. And then there could be others, depending on what type of statistical analysis you're going to do. And so when we're looking at environmental data, we have very little of that. We don't have independent observations, because when we collect data, we collect them in time series, which makes them dependent in time or we can collect them in space, which makes them spatially dependent. Or maybe they have seasonality, which is a specific kind of temporal dependence. We typically don't have nice distributions. I work a lot with concentrations, so they would be skewed. That's not really a problem. We can handle that. It's, we have ways to transform and do things. So not so serious, but maybe most important is that we don't like to assume linear relationships. We usually have much more complex systems, much more complex relationships, and that's important to take into consideration. And then, of course, we have the typical problems with observations under the detection limit. Maybe we have missing values, we have outliers, we have a lot of different things that need to be taken into account. And so what are the consequences of environmental data being a little bit different? Well, we typically will deviate from the theoretical distributions that we like to use, and it will also be quite difficult to estimate correct standard errors because we have dependencies in the data, and the data that we build our estimations on, they are quite limited. And so we get problems when we want to do the traditional hypothesis testing. The good thing is that we are not really interested in hypothesis testing in many cases. It can be relevant, but much more relevant is hypothesis generating. We want to understand the systems that we are studying. We want to find patterns, and we want to observe a complex system and find new knowledge in these. So my subject is called biometry, and it's often explained to be statistics with application in biological systems. And for me, that means that we want to extract relevant information based on data, and data that then describes complex processes or complex systems. And while we are doing that, we want to rely on so few assumptions as possible. We want to choose data-driven approaches if it's possible. And then we want to summarize the data. We want to visualize it, and we want to present it for our stakeholders, and we also want to include uncertainties. And stakeholders in my case would be then environmental scientists, maybe environmental agencies. So it comes down to the questions: what do we want to extract? What do we dare to assume? And how are we going to package the whole thing so that it's possible to communicate to other people? And I'll show you this in an example. We're going to ask the question, is there a trend? So we're going to the if. And that's, of course, a typical hypothesis testing question. I want to know, is there a trend, yes or no? And we could do that then with quite old methods. They have been around for 40, 50 years. We would like to extract information about the presence of a trend, which we would then package as a p-value or a yes-no answer. We would at the same time like to correct for certain data characteristics, for example, the seasonality and this autocorrelation in data. So that's the temporal correlation that we have because we have a time series. And we want to assume as little as possible. And there's a hugely popular trend test that is called Mann-Kendall test, which is used a lot because it doesn't assume a lot of specific things. It assumes that the trend is monotone, and it has no assumption about the data distribution. We could use linear regression, but then we would add assumptions, which we usually don't like to do. And so we have an example here, sulfate in Ljusnan. We see that there is a clear downward trend. We can do a Mann-Kendall test. We can extract the p-value, which is actually 0 here. So we have a very clear, significant downward trend. And that's not so surprising because we know that sulfate levels have dropped dramatically in the 1990s. So whenever we include the 1990s in our time series analysis, we'll get a downward trend. If we remove them, maybe we are interested in only the last 15 years, then we would get a different result. The trend would not be significant. There's no change in this time period. And this actually leads us to an additional problem here, because we have an additional assumption that we are not really aware of, which is that the time frame that we're doing the trend test on actually matters. So depending on which time frame I choose, I get different results. And that does then mean that I need to be sure that the time frame that I'm choosing is actually relevant for my question, instead of just saying that I have data from 1984 onwards, and therefore I do the analysis on the entire time frame. So the time frame is important. I asked a very simple question. I got a very simple answer, summarized, packaged in a p-value. But I also lose a lot of information on the way. So because I asked the simple question, I don't know now if the change is gradual or is it sudden. Does it happen over the entire time period or only during a limited time? And wouldn't we really want to have a statistical method that is not dependent on the time frame, so that I don't add on my expectations on the analysis and make it dependent on that? And therefore, we really would like to identify when the changes occur, not so much if they occur. So we're going on to the when. And the when can be quite easily answered by using smoothing methods. There's a large model class here that can be used, generalized additive models. They have become really popular also in environmental analysis because they're data-driven and they don't rely on assumptions. They have been around for a long time, but are more and more popular now because R has a huge package where it can do lots of things. So we're going to use a smoother to model our temporal trends. And that would look like this. We have some response variable, which would typically be our concentration, sulfate. We have an overall mean, which is called mu. And then we have a change, a smooth change over time, which is then completely data-driven, so completely dependent on data. I don't put any restrictions on that. And then we have the typical error term. Just as before, for the main candle test, we need to correct for a couple of different things. We need to correct for seasonality, because that's very often present. So we would add then, for example, a smoother that describes this seasonal variation, a function on months or Julian day, which can be easily included here as a smoother as well, which would be a circular smoother then, because we want, of course, the seasonal variation go in a circular wave. And then we have the autocorrelation. We would need to correct for that as well, which means that we put an extra term on the error term that describes then that this is a time series, and we correct for the correlation in time. And when we do this, we end up with a form like this. I hope you can see it. We have a smooth trend curve that is indicated here. The seasonal variation is removed and the autocorrelation is taken into account. The problem with this is that I need to show you the entire plot. I mean, it's not really compromised, it's not really packaged in a good way. I need to show you the entire plot, you see the data, and then this smooth doesn't really add a lot to understanding what happened. So what we would really like to do here is that we would like to extract what is important, and what is important is when do the large changes happen. And we can do that by looking at the derivative of the trend. So we have an estimated trend curve here, and we can take the derivative of this, which then gives us an estimate of the trend slope. So if the derivative is highly positive, we have an increasing trend. If it's highly negative, we have a decreasing trend. And we can then do that point-wise, because it's a smooth, we can determine it for each time point, which means that we can identify when the trend is the strongest or when there's a large signal-to-noise ratio, so when the trend is strong compared to how much variation we have in the data. And we have the uncertainty of that, and we can do some kind of hypothesis testing. So the hypothesis testing is not interesting in itself, but it can help us visualize results. And then we would get something like this. So the same curve, but I have indicated in blue here when the trend is statistically significant according to some measure. And it's yellow then when we have no trend or we only have a small trend, which is then not significant. And so we could use this information, this color coding, and just save that instead of showing you the entire plot. I can just I keep that information, and then I look at another time series, and there's a similar trend. It starts earlier, it maybe goes a little bit longer. I save that information, and then I have a third one, and then I get something that looks like this, which gives me information about several series at the same time. It gives me the information when are trends significant, when are they not, are they upwards, are they downwards, and I can get a fast overview over my data material. And obviously, because I have the results here for the individual series, I can also sort the series in some manner that makes sense to me. For example, geographically, in this case, they go from north to south, which makes it easy that I also include the where are trends happening. So we're going to the where. And I show you this same plot again, but I've changed it a little bit. What you see now is instead of this yes-no answer, you see the p-value, so I get a little bit more detail on this plot. And then we can study this. And one thing that we see very clearly here is we have one series that doesn't really fit in. And then we go back and see what happens to this series. Well, it shows that we have a local pollution source. So it doesn't really fit into this because all the other sites did not have local pollutions like this. We also see that we have a large drop in sulfate in the 1990s. We already knew that. It's seen in a lot of series, especially in the south of Sweden, which is not surprising because that's where the deposition happened, and then the deposition was decreased, and we see the result of that. Similarly, but a little bit more difficult to see, is we have a couple of red ones here in the end of the series. The series typically look like this. We have a slight increase here, increased levels. We also very often observe a spike, and the spike is typically observed in the autumn of 2018. So it could be an effect of the very really dry and warm summer in 2018. We see it in several series. My role as a statistician is finished here. I will leave that over to my colleagues at the environmental science environmental science experts, who then would use this hypothesis and check and see if they can find the reason why this is observed. But I could also say that, well, what I see is a couple of series that show very similar behavior. They lie closely to each other geographically. They are actually all in Värmland. And maybe I want to do an in-depth statistical analysis to see a little bit better what happens in these series. And then I could, of course, implement that in my statistical model. So I could, I still have the overall time trend here, but now it's valid for all the series that I'm looking at, which were 8 or 9 series at the same time. And then I include a random factor site, which allows the different sites to behave slightly different, but not too much. And I force the smoothness of the overall trend and the smoothness of the individual deviations to be the same by setting a penalty factor that gives me then similarly smooth functions, which would be something like this. So we have the overall trend here. We see the strong decline in the late 1990s, a little bit of a plateau, an additional decrease in sulfate until maybe 2015, and then this little bit of increase and decrease in the end, which could or could not depend on what happened in 2018. And then we have the individual series, which look very much the same. We see the same structure there, maybe because we assume that the same structure is there and we force the model to reveal that, but I've tested it also without that assumption, and it's actually working. What we also see is that there is more variation in the beginning of the series than in the end of the series, which is also quite reasonable, because in the beginning we had different pressures from deposition, and then when the deposition pressure is removed, we end up with series that are more alike each other. So, perfect. I can do a lot of stuff. I have really nice time series, environmental monitoring programs that produce series with monthly data, a lot of questions. So it's just like use statistics and do things. But then not all environmental monitoring programs give us data that looks like this. We have also environmental monitoring data that gives us time series that look like this. And then we could say, well, unfortunately, there's nothing we can do with statistics because we cannot fit a model. But that would be boring. So we have a series here, Lillgårdsträsket. It's in the north of Sweden, and it's actually part of the Swedish Lake Survey. And the Swedish Lake Survey, Omdrevssjöprogrammet, includes a lot of different lakes. But each lake is only observed once each 6 years. So we get sparse data, but we get a lot of data because we have a lot of lakes. And obviously we cannot use conventional trend analysis methods because they don't work on the site with only 2 or 3 observations. So we need to do something else, which means that we need to consider what can we assume. And we can, of course, assume the same thing as for Värmland, that stations that are close to each other also exhibit similar trends. And that we can assume if the trends can be expected to be driven by large-scale phenomena, deposition, climate change, regional scale, land use changes, things like that. So if we have something like that, we think that deposition influences our trends, then we could estimate trends within a geographical window. Maybe we have to make other assumptions on the way just to make it work. We need to be aware of that. But I mean, data is limited. We need to find a way to make things work. And in this case, we need to assume that trends are linear, at least during shorter time periods. And even for this, there are statistical methods already available. They have been around, and again, being more popular as they become available in R. This specific case does not work for trend analysis. It works for other cases. So we had to tweak it a little bit and make some pre-processing of the data, but it was still quite straightforward. And what we do then is that we have our lakes, and especially we have our Lillgårdsträsket here in northern Sweden, and we put a geographical window around that. And within this geographical window we have a couple of lakes, maybe 20 in this case. And then we see that several of these exhibit the downward trend that we saw before as well. Others do not. Some show an upward trend in the later years. And now we could fit a statistical model on this data because now we have more observations. We would typically do some weighted regression then, as the geographically weighted regression allows us to give more weight to lakes that lie closer to the target lake and less weight to lakes that are further from this lake. And then we get a trend estimate here. We do some kind of linear regression. We get a slope estimate. And then we move the window to the next lake. And for the next lake, we make a new window. We get new data. We make a new model. And then we can move this window over entire Sweden. And we end up with something like that. And then we see here, Lillgårdsträsket was situated somewhere here. No? Yeah. but you see it anyway, it's blue, downward trends. As time goes on, we don't see this blue anymore. It's not downward going anymore. Instead, we see then in southeastern Sweden, we see an increase in sulfate. As years go by, it gets more and more red. So we get information from this very sparse data by assuming geographical windows. And we see here then, well, we see how trends change over time, and we see how trends change over a geographical area, which means then that we get quite a lot of knowledge of what is happening, and a lot of hypotheses that we generate. And understanding when and where things happen also brings us to why things happen, because again, my colleagues in environmental science will make some sense out of that, even if I maybe don't. So the question is, why are trends happening? And that's really something that we cannot answer with statistics. It needs the in-depth understanding of environmental scientists of the system that we are studying. But I can still give some input to support any hypothesis generation. For example, we could just simply plot several variables at the same time and see if there's an overlap or if there is differences. So when certain trends go up or certain variables go up, others go down. Don't know. We could also include explanatory variables in trend analysis methods. Call it partial trends. So we see there is a trend and then we add an additional variable and there's no longer a trend. That would mean that this variable actually forces the trend, and we see that it's the reason that we have observed a trend from the beginning. And we could do that with these geographically weighted regression models. But there's a certain problem because it's computationally very expensive. And we have what I'm using now, approximately 4,000 lakes, which means 4,000 geographical windows. Actually, it should be more than 5,000 if I use all the data. I might be interested in temporal windows. I need to find the best size of a geographical window by cross-validation, which is computer intensive on its own. And we need to fit the same models for 3 individual variables in the same model, which we typically do by backfitting, which is computationally expensive as well. So I tried that on 4,400 sites, and I found then when I tried this, also on smaller sample sizes, 4,400 sites, I would need approximately 10 hours to run a model like this, which is okay. I mean, I can run it overnight, that works well. The problem is that I don't have 1,400 lakes. I have more than 4,000, maybe 5,000. And then I could make a prediction. And it would end me at, well, that would maybe take 3 weeks to run. And that's only one model. I don't even know if it's a reasonable model. I would need to test different ones. So the next step would then be to either say, well, I have to skip this line of research because it's just simply isn't feasible. Or I can look at what I can do in terms of runtime. Because whatever I've done here, I do on my own computer. I can do it in parallel, but it's still only an old standard PC. So obviously, the first step would be to try it on OpenMax, which is Uppsala University's supercomputer. There I have more cores to work with. And our estimation is that we might get it down to 1.5 weeks. It's still not really good. So what we do instead would then be to look at how the things are programmed and if we can improve things within the program. And actually we found quite a lot of things that can be done there, especially on how memory is used, and maybe could use another programming language. And the overall goal is then to bring it down to maybe 20 minutes, and I think that's feasible. And then we could start actually working with these models and see if they are applicable in real life applications and if we can actually use them, because that's not sure. I mean, we make a lot of assumptions and the relationship might not be there that we're looking for. But that's a typical type of research. I mean, we start with an idea. We see, is there already some program code that we can work with? Can we improve it? Do we need to pre-process data? What do we get out? Can we interpret what we get? And then, in the end, how can we make this available for researchers, as the research community? Which brings us to the future, because there are, of course, a lot of such programs going on. We, for example, have been working with looking at not only the means, but the extremes in data. For example, are high values getting higher, or episodes of acidic low values more frequent? And that's mathematically, it's not a problem at all. It's easy to be done, but we're observing data on a monthly or bi-weekly basis, which means that we're missing out on the tops and the bottoms. And so we would need to do more studying to see if we can actually recommend to use these methods on real-life data, or if we need to wait until high-frequency sensor data is available. And we could also like to model changes in seasonality, or we could like to model changes in relationships between concentration and, for example, runoff, to see if they indicate that the pollution source changes or that management practices have an effect. So if we do things on our fields that should stop the washout, the leakage of nutrients to the water, can we observe that in the concentration discharge relationship? And we have published that, but it needs more work to be done to see if it actually work in practice, or if the changes that we observe is so small that we cannot really draw any conclusions. And then what is most important right now is working with the why. So decision support for, or hypothesis generating for why things change, or why, yeah. And for this we have two foremost projects ongoing. The first one is on the lake survey, so we're working further on this sparse data set to see what we can get out of there. And the second one is more on the classical time series. And so what we like to find here is really some ways to present data so that we can understand better how different variables work together and how they are connected to each other with the limited data that we have available. And if you look at it like in a broader sense, well, Sweden has 11 Swedish environmental monitoring programs. There are a lot of sub-programs. There's a lot of data. New data is produced each year. There's also a lot of existing statistical methodology, and maybe even more if we count the ones that don't fit automatically but need to be adjusted a little bit, or need to be sped up or adjusted to fit the data that we have. And I think it's really important to fill this gap, because there's a huge gap. So much more could be done in environmental statistics with methodology that is already available. And I think SLU has a central role here, because we host a lot of this data. So I think the competencies at SLU, this is here we need to do this work. We cannot rely internationally on researchers because the data in other countries look different. So it's our task to fill this gap. And that brings me to the end of my presentation. And there I just want to say that I could not have done this by myself. I'm very dependent on my colleagues that work with environmental science and other persons. And especially for this presentation, I don't think I showed you anything that didn't come to me as a question or task or a problem posed by my colleague Jens. So special thanks to Jens for having a lot of problems. Also special thanks to my younger colleagues, Staffan, Leonardo and Hjalmar, for doing a lot of the hardcore programming, which I also cannot do by myself. And thanks to my colleagues in statistics and at my 3 departments, which I think are my home places. Thank you.